9.5, I'd like us to use StatCrunch in order to do this calculation. So this is based on a survey conducted by Gerber of 1,000 women aged 18 to 24 who had children under the age of 2 years. Of those surveyed, 400 had created a social media account for their babies before their first birthday. So assuming it's reasonable to regard the sample as representative of the population of millennial moms, construct an estimate of all millennial moms who created a social media account for their babies before their first birthday. Now, why would Gerber be interested in this? Well, they might want to see if they need to start targeting these babies' profiles for ads. So let's go over to StatCrunch and see how we can get our confidence interval there. We're going to start with a new data table and go to Stat, and we're dealing with proportions in this chapter, and we're dealing with just one sample proportions. Now, we don't have the raw data right now. We don't have a list of all of the actual responses. We just have the summary. So we'll go to summary, and this is going to ask for the number of successes. And here there were 400 moms out of the 1,000 who had created a social media profile for their babies. And we're doing a confidence interval, and we did not decide what level that we were supposed to do. So let's do one different. Let's do 90%. So that's going to have a critical Z value of 1.645, and that's going to be calculated into this StatCrunch programming. So you don't even have to worry about that when you're using StatCrunch. Simply click compute, and you'll get your responses. The answers are here in the lower limit and the upper limit. You also can get your sample proportion right here. Your p hat is 0.4. The standard error, remember that is that square root of p hat 1 minus p hat over n. Now the margin of error is that number multiplied by the critical Z value. That's not given in the output, but the calculation is done for us. And so those would be our upper and lower limit for this particular confidence interval. So let's fill in our notes with that. So if we do a 90% confidence interval or confidence level, or p hat, often I'll go ahead and give p hat even if I've used technology, and 3 or 4 decimal places is usually plenty, and so we have 0.397 to 0.427. Now we could interpret this. We are 90% confident that the true proportion of millennial moms who've created a social media account for their babies before their first birthday is between 39.7% and 42.5%. So what if we are looking to do a particular margin of error? So maybe we want to make sure that we are within a certain amount of the true proportion. I could give you a confidence interval that was, the answer is between 1% and 99%, and that's not going to be very helpful. So you might want to say, hey, I need to have my estimate to be within a certain percentage of the true proportion. And so we'll use that with these formulas. You take, if you have an estimate for P, if you know from a previous study or you have an idea of what it might be, then you would do your P times 1 minus P, and then 1.96 divided by the particular margin of error that you're looking for as a decimal, and you square that. Now, if you don't have an estimate for P, then you do need to use the worst case scenario, which is by putting that 0.25 there. Now, quick note, you always have to round up. This is giving you the minimum sample size. And so if you have 100.0001, that is a little bit more than 100, so you would have to round up to 101. So your typical rounding rules don't apply. You always round up. So in example 9.6, we see researchers in England are leading a study to determine whether dogs can really identify the presence of cancer by sniffing urine samples. Okay, this is a study that's really going on. What or how many different urine specimens should be used if you want to estimate the long-run proportion of correct identifications within a margin of error of 0.1? And so here, they did not give us a percent, they gave us the decimals, so we don't have to do any conversions. Our sample size, since we don't have an estimate for P, we have to use this 0.25. We'll do 1.96 divided by this 0.1 margin of error, since it was already given to us as a decimal. You square that, and you get 96.04, but you can't have part of a sample size So this would be 97 samples.